Yeah.
I can go. All right. Hello, everyone. I'm Madison. I'm from the Bio-Inspired Circuits and Systems Lab in Groningen. I guess when I'm explaining this, a lot of the motivation for why I did this comes from wanting to come up with architectures that can be built and robustly function on neuromorphic hardware, which can be a bit crappy at times. So you need very robust algorithms, which of course smells of VSAs. Vector symbolic finite state machines in attractor neural networks. A very brief overall explanation is that I wanted to take a very conventional attractor network model, so the Hopfield network, and then make as few changes to it as possible, and indeed as few biologically implausible changes to it as possible, so that you could kind of trick a Hopfield model into functioning as an arbitrary finite state machine. So the states within your state machine will now be represented by attractors within your Hopfield network, and by giving sequences of stimuli to your attractor network, you should be able to trigger corresponding transitions between your attractor states in your Hopfield network. So there were animations here, but no longer. If you imagine, they're coming through iteratively. So my overall argument is that, and I think it's not a kind of a horrific statement to say that biological units, whether those be neurons or synapses, are quite noisy. And one of our kind of favorite models to get around this noisiness and have kind of robust cognitive dynamics despite these noisiness and non-idealities is to use attractor networks. And then going a bit further, what we know from kind of neural recordings is that many cognitive processes can be modeled as an itineracy between these different attractor states. But my claim is that there doesn't yet exist a nice kind of adaptation of the Hopfield network such that it can implement these kind of attractor transition functionalities without bringing stuff in like delayed synapses or whatever. So that's one half of why I did this. The other half of it is, as I said, neuromorphic. We use funny devices, so whether those be analog neurons, analog synapses, or these beyond CMOS memory system technologies, which everyone's been talking about. As great as they have a certain degree of noise and non-idealities associated with them. So one way to get around this, attractor networks, and then if this all works, we can then build attractor-based state machines with them, despite how noisy they may be. So I'm going to very briefly give an introduction to Hopfield networks. So they are you can represent one as a large binary vector, so actually bipolar, I guess. So each neuron is plus or minus 1, and there are n of them. And then it is equipped with an asynchronous or asynchronous update rule, whereby on every time step, the neurons project back to themselves via a recurrent weights matrix W. And then they then have a sign activation function. So any neuron that receives overall positive input goes to a +1 state, and any input that receives overall negative input goes to a -1 state. And then what we know is that just by iterating through this rule, you descend the energy function given by that. So a quadratic product of your network state and your weights matrix. But the question is then, how do we construct our weights matrix in order to do something useful? So if we pretend we have some set of uncorrelated hypervectors x nu, then if we construct our weights matrix to be a sum of outer products of these hypervectors, this is just a Hebbian learning rule, then your energy surface will look like a load of parabolic wells around the states that you've stored. What this means is that you could start your network off in kind of some corrupted state, so it's not exactly at the bottom of the well. That's not me. You can start off in some corrupted state that isn't at the bottom of the well, and just by iterating through, it will descend to the bottom of the well, and that's what we can sometimes call pattern completion. Oh, it is working, okay. So here we see some pretty GIFs I found online of someone just showing, look, this is pattern completion working. So they have a Hopfield network, they've stored their 3 patterns, so a bike, some people, some M&Ms, and whenever it flashes, it's being initialized in a kind of noisy state, but then just by iterating through with the weights matrix and then sign activation function, it converges on the, I guess, clean patterns. So that's cool. Now, my kind of weird claim is that if we squint very hard, it kind of looks like a state machine, kind of, very kind of. So if we say we have these three states, so a stable bike state, a stable M&M state, and a people state, then we can say that if you give your network a very strong input that corresponds to, say, the people state, the network will switch to representing that attractor. And conversely, if it's in the people state, you can give some input that looks like the bike image, and it will switch to that one. But as you might notice, it's a really crap state machine, because the state which you go to is dependent entirely on the input you give to it. As in, you say, here's an input of people, you go to the people state, great. As in, that. If you were to try and use this as like computational primitive, you're massively limited in kind of how useful it can be. So we'd like it if we could trick a Hopfield network into representing kind of a more general finite state machine. So I can zoom now. If, for example, we try to embed one like this, so we've got 6 states now, and let's say we have some stimulus father is, then we want that when our network is in the Zeus state, so it's sitting in this Zeus attractor, we give the input father is, it goes to Chronos. But if it's already in Chronos and we give the input father is, then it goes to the attractor state Uranus. And of course, this is something you wouldn't be able to get out of a normal Hopfield network. So very quickly explain how it works. Again, imagine each line came nicely and it wasn't just a wall of equations. So the first change we make to the Hopfield network is just to add these edge matrices. The terms in the top left, normally they came, whatever. The terms on the top left are your normal attractor terms that Mr. Hopfield had. But then every edge term looks like this. So for every edge in our state machine that we want to kind of embed within our network, we have an associated attractor we want to start at, so that's our source vector. An attractor network we want to go, an attractor we want to go to, that's our target vector, and some stimulus S that we want to cause the transition. And we're binding on the right our kind of our source attractor state and our stimulus via just Hadamard element-wise multiplication. And then the other small change we make to the Hopfield network's functionality is how we model input to the network. So for reasons that I could go into, but it's not very interesting, the way we model input to the network in order to realize the functionality we want is to model it as an effective masking operation. So we say that if we have some input vector S input that we would like to give as input to our network, then any neuron for which S is negative, we want to be set to 0. So such that only the neurons for which S is +1 are allowed to, I guess, partake in the computation. Yes, the way we do that, just quite simply, is say, right, take our bipolar S vector, put it into a Heaviside function, that's obviously that just converts it to binary, and then apply it as a multiplicative mask, again, just via Hadamard multiplication. And the idea is that this is an operation that you could easily realize in an asynchronous system, because all you're doing is telling half of your neurons to die, basically. It's quite reasonable. And then, right, the problem is this, again, this was animated, but this is difficult, right? So all the terms in black, they are our weights matrix. And the point is that our postsynaptic sum, so if we want to work out what the dynamics are going to do, we need to work out what our weights matrix times by some attractor state is, because that gives what your postsynaptic sum is and thus what state your network transitions to. So in very light gray, imagine that just appeared. We can now kind of work out what the postsynaptic sum is going to look like just by applying simple hyperdimensional arithmetic. And the point is, all the terms on the right, if you're just sitting in some attractor state, don't produce any significant overlap, because you see here, these terms here produce 0 inner product with our X mu state because it's bound with some stimulus state, which means that as long as you're not doing anything funny, only the terms on the left matter, you have a normal Hopfield network. If we now ask what happens if we're in some yeah, so top line first. If we now say that at some time t, we're in some source state and we're masking our system with some vector s, which corresponds to a stimulus associated with a certain edge, then within our summation over edge terms on the second line, the sum over eta, there may be one term within that edge summation which has a non-negligible overlap, because we have an x source bound with a stimulus that's being dotted with our state that we're currently in, which may be the x source state being masked with the correct stimulus. And what happens then is that one term from our edge term summation pops out. So this is the term in the brackets. And then finally, what pops out is our target state, which is where we want to go, basically. So this is simply explaining overall how the mechanism works. So we've added some edge matrices. We mask our system with a certain stimulus when we want to cause certain transitions. And just by the hyperdimensional arithmetic, you get the correct states being projected out. Here we see it working, so that's quite nice. So if we start off in some state, in the state Hades, for example, we give the input, and it's a bit small, sorry. We give the input father is, it transitions to the state Kronos. Give the input father is, again, it goes to the state Uranus. And there's a sequence of input, it does them correctly. So that's nice. I want to get onto the fun stuff. Then the claim is that you can then do, you can do entirely general finite state machine emulation, as long as the state machine you want to embed isn't too big, obviously, because there will be limits on how many states you can store before your attractor dynamics break down, for example. There are a few extra quirks that I could mention to describe really how we get entirely general state machine emulation. For example, needing to add a new attractor state for every edge within our state machine, but that's not very interesting. I've also cut some slides because I wanted to speed through to the fun stuff. But basically, I could have shown you that this system is very robust, but you just have to trust me for now. So you can, for example, take your weights matrix, binarize it, abuse it by adding a load of noise. Your network will still function perfectly. You can make it very sparse, it will still work. You can give inputs that are asynchronous, it will still work, or you can have neuron updates that are asynchronous and it will still work. So this is where the argument of a kind of robustness and these sorts of algorithms can be implemented in neuromorphic hardware, arguably a biological system, comes in. Yes, that's that. But then the fun stuff is generalizing it then to continuum. So basically what I wanted to do is, instead of having a discrete set of states that we can transition between by giving certain stimuli, I instead want to have a sheet of or some manifold of stable states, such that you can push your neural state around this manifold, hopefully slowly and stably. So the first thing you have to do, of course, is to go from having some finite set of states x nu to having a smooth parameterization of your state. And so for that, I'm just using Hadamard fractional power encoding. And I guess, as quite a lot of you already know, that how it works, as in you parameterize a state via e to the I omega times by whatever value you're encoding. And then the similarity between any of your states has an associated kernel function, which is given by the Fourier transform of your of the probability distribution of your omegas. But I'm running out of time, so I'm not going to explain that very well. Yes. The other thing we need to do to generate this network to continuous manifolds is to so we've done the one on the top left. We've taken our network state and said, right, you be continuous and smooth. The other thing we need to do is swap out our neuron activation function, so in the bottom left, from being a sign activation function to instead being, I guess, the complex equivalent. And that is that on any time step, your neuron inherits the phase of its postsynaptic input, rather than just saying, are you greater or less than 0. The other two changes you need to make are, of course, what was a sum over states, you now generalize to an integral over states, and your edge terms which we added for every edge within our finite state machine also has an integral analog. So if we were to try and store, say, a 2D plane of states, we would have one set of terms in the top left that would describe our attractor surface. So we're just saying, right, this is a 2D integral over some 2D hypervector, as in it's a big dimensional hypervector, but it's parameterized by two values. And then you can kind of add arbitrary vector fields on your attractor plane, which activate whenever a stimulus is present. So the idea is we want, okay, when you mask your system using the stimulus 1, you want, say, your neural state to move in that direction or the other one, or some stimulus 3, someone suggested this, that a swirly one would be nice. We have a swirly one. Yeah, the idea is you should be able to just store arbitrary vector fields on this attractor surface using the VFA framework. So we see that working, that's nice. So this is looking at the overlap of our network state with any state on our like our 2D surface of states that we're interested in. And you can see just by masking the system with different stimuli, your attractor network will indeed move around your attractor plane, which is quite nice. And like, yeah, your circular motions are working, your orthogonal ones are working. Speed running now, you could do the same with funny surfaces. So let's embed a sphere, see if that works. The answer is yes. Yeah, there we go. It's a bit framey because it's going through Zoom. But the idea is hopefully this should extend to embedding, say, entirely arbitrary smooth manifolds within an attractor network. Why? I don't know. You can argue that it'd be useful for, say, path integration tasks. But what the cognitive uses of this would be, I'm very open for collaboration if anyone has any good ideas. Yes, so my overall conclusions are, the overall conclusion is that I think VSAs can be very useful for getting robust computation out of a dynamical system where your dynamical system is made out of really crappy components, which I hope you've been somewhat convinced by. The thing that I've showed fairly well is that you can embed using VSA techniques. You can trick, say, a Hopfield network into being any state machine, and hopefully you're somewhat convinced that this does generalize to continuous attractor networks and pushing your neural state around a continuous manifold. Yes, that's that. Thank you very much.
Maybe a couple of quick.
Oh,
Who was that? I did. I think very quick.
Dennis.
But since you're in the hardware and neuromorphic, is there anyone trying to actually build this thing hardware? Is there a side ideas or
not related exactly to me. I'm trying to get one going at the moment, as in someone's got a largish memory stiff crossbar. I'm trying to do that. But yeah, I mean, at the end of the day, it will boil down to just doing kind of a matrix vector multiplication, applying a masking operation maybe, and then seeing how your network switches between the states. But at the moment, I haven't built this, but I'm trying to trick someone else into building it. Yeah. Questions?
Yeah, I'd love to chat with you more.
Please.
Just a quick question for now. Does the finite state machine with the integrator have a Lyapunov function?
I think the problem is it won't, because my weights matrix is no longer symmetric. So, I mean, I could very easily design a system where, of course, it starts going around in circles. And so you can't really have a Lyapunov function for that. But I wish there was, because it would make it much more elegant. So, no. Yeah, any other questions, or are we done?
Oh, yeah, really less up. Yeah. Well, maybe. Yeah, it's like this. I think we
finished with the questions to you.
Lovely job, Lee.
Thank you once again.